Hey there, hackers! Today I will tell you about the absolutely amazing path function. This has just stabilized in Uiua recently. Previously it was called A star. It is really a rare feature that a programming language has a fully fledged pathfinding mechanism built into its core. With a single keyword we can invoke the Dijkstra's algorithm or even solve more advanced optimization tasks, tackle search problems, work with graphs or even images. In this video, I will use it to solve the advent of code datetime problem. The challenge itself contains a bunch of numbers placed on a rectangular map. These represent hiking trails. 0 is the lowest point or the trail head, 9 is the highest point or the trail finish. We can only progress in any of the four main directions, up, down, left, right, and only when the next step is exactly one level higher. We need to find all the trails that start from all the zeros. Each part of the task uses a different scoring mechanism. Let's take a look at the pass function, which gives the principal idea for the solution. Contrary to other Uiua functions that tend to have a very straightforward arity, the pass function actually has some variations, different ways to use it. We will use its simplest form in this challenge, but it's good to know about the other options. Maybe we can apply it differently in another puzzle. It has at least two function arguments and at least one value argument. The value is the starting state of the problem. We may call it the first node. It represents the initial object state or position. In our case, it will be one of the coordinates for the trailhead, which has a 0 value. Then the first function tells the program how to get from one node to the next. So it is the neighbor function. In our case, it must calculate the coordinates of the valid next steps on the path to the hilltop. Each of these nodes will be followed during the optimization to figure out the shortest path to the goal. Optionally, we can give a cost array as well, which has the same number of values as the return value of the neighbor function. In our case, moving any direction costs the same, so we will skip this. The second function is the goal function. It must determine from the state if the objective has been reached. In our case, the problem is solved when we reach a node with the value of 9. Now there is also one more possibility to add a heuristic function. The purpose of this is to give some sort of cost calculation based on which the algorithm would try to pick the cheapest path first. However, this will not impact the outcome, potentially just speed up how fast the solution can be reached. In this problem we will not use it. It's also interesting that the path will give us two results: the lowest cost that can be achieved and also all the possible ways how that result can be reached, in a boxed array which contains all steps of all the routes. Maybe we are only interested in the cost or in one single route or the number of routes. All of this can be extracted from these outputs. Now it should be clear what we need to do. Let's start writing some code. Let's copy the sample input to the pad and convert it to a multi-line string. Parsing the input will be quite easy because the shape is regular. After marking the new lines, we can just parse each character to convert everything to numeric digits. If we are keen on optimizing for speed, a nice tip is that character arithmetic is even cheaper than parsing. Subtracting the character 0 achieves the same effect. I will save the data in memory, binding it to the name grid. The starting points of the trail can be easily found just comparing the values with 0 and using the where function to retrieve the coordinate pairs. The first pass starts in row 0, column 2. Now the next thing is to figure out how to move on the hill to the next position. We can move one tile in any straight direction. So moving to the right means increasing the column number by 1, and this is done by adding the array 0, 1 to the current coordinates. We could just spell out the array of the possible offsets. After all, it's just 8 numbers arranged in a 2D matrix. But we might just as well compose it with a Viva function. Here's one of many ways to do it. Start with a range of 2 and combine with itself in a table using the equals sign to build an identity matrix. Make another copy and take its negative. Plus and minus 0 are actually the same. Then finally, join both squares to form a 4 times 2 array. They are our offset that can be added to any coordinate to calculate the next step. It is a constant, but we can still bind it to a name. Let's try how it works. Given a pair of coordinates 0, 2, I push this matrix to the stack and add it. The problem is that by default, Viva is trying to do pairwise addition, so fixing the current array first will solve this, and it will be paired with each row of the offset. We can see the possible new coordinates. Actually, one of the numbers is negative, and we may even get numbers that is too large to be a valid index. But no worries, we will deal with this later. We can use this as a starting point to evaluate where we can go next. This will be our neighbor function in the pathfinding algorithm. This function will take the current coordinates and the map itself, the array of numbers we have already parsed, and it will return an array of the possible coordinates which are the next level of the trail. Conceptually, we want to get to the adjacent map positions, check their height, and compare it with the current one. They are valid if they are incremented by 1. We need to be careful with staying inside the bounds of the map too. We can use pick to look up the height and the keep function to filter coordinates. Now it might get a little challenging to shuffle the values around on the stack because each function will consume them. So it's always good to be familiar with some of the stack modifiers. Using them can save some effort of manually copying or flipping the values one by one. We already figured out to calculate the next coordinates. If we use the below modifier here, we can actually duplicate both of the initial arguments, and even though these functions did not even touch the grid itself, it is also getting copied. Now we have 4 values on the stack. Let's use pick to read the height of the surrounding positions. It's interesting to observe that 9, 1, 1 are correct, but the 4 comes from the bottom line because the index of -1 wrapped around, rather than causing an error. Obviously this is wrong, but the good news is that we can easily fix it by adding a fill value to pick. This will be selected whenever the index is out of bounds. We could fill with 0 because it is actually never a valid next step, but using infinity gives better optics. In either case we can compare. The current position has the height of 0, but keep in mind this function will be invoked at every step of the way, so we have to determine the current height dynamically. And now that we position the arguments on the stack like this, it's enough to use both before the pick, and at the same time both pairs of values will be processed. Pick works with a single index value as well as an array of proper indices. Now our coordinates are also consumed, but we will actually need those for the next step. Before the pick operation, they were the first value on the stack, so here we can use the off modifier to copy them under the values that are being created. Off is still experimental, so we need to add this tag here in the comment. We are almost done. Now we need to compare the potential heights with the current one. The difference can only be 1, so at this point we can simply subtract 1 from the potential next heights and use equals to compare. The result is a mask that we can apply on the coordinates with the keep function. What this means is that from the starting position we can take 2 ways, one down and one to the right. Our hikes function is now ready. One more component to start pathfinding is the goal function. This will also take the current coordinate and the grid. And it's very simple, we have to compare the height with 9. When we reach the top, the algorithm is finished. Finally, we can try the optimization on the first trailhead. We get the number 9, which is the total minimum cost. As we did not provide any cost, 1 is used for each step. And all the possible paths that lead to any of the heights from the first position. We can discard the cost because we cannot use it in this problem, and I will call this the climb function that gives us all the optimal solutions. The challenge is asking us to determine the score of each trailhead, and it is the number of different peaks that can be reached from the particular starting point. So we can take the very last value from each solution using the content operator to penetrate the boxes and deduplicate to find only the unique points. Finally, the length function will count them. The score of the first trailhead is 5. Now all we have left is run this for all the different trailheads, and we only need a tiny fix for it to add another dimension to the grid before we start. The second part of the challenge is even easier to accomplish with the pass function, because the rating is just the total number of trails that start at the specific position. And we just need to count them with the length function. So that's the solution for part 2. Pass is an incredibly powerful tool, and we don't even need to add any library. It's built right into Uiua. Apart from AOC challenges, it can be useful for many different types of problems. I really enjoy exploring the richness of Uiua, and solving such tasks with so little effort. It's very rewarding. Don't forget to press those YouTube buttons if you like this video, and check back for the next one. See you later!